Oh hi, how are you? Happy Sunday evening, which is not my favorite time of the week because, well, first of all, it's Sunday evening, so weekend is over, and second, typically I wake up around like what 4 p.m. on Sunday because I take a long nap during Sunday, and after a long nap, there's this bitter aftertaste. Ugh. You know, have you ever wondered why babies cry when they wake up? Because there's this bitter aftertaste after a long nap, and it's not pleasant. Ah. Some, uh. So what do I do when after I wake up on Sunday, long nap on Sunday afternoon? I eat berries, strawberries, blueberries, because I need something sweet to get rid of that bitter aftertaste of long Sunday afternoon nap. And I eat berries, strawberries, blueberries, raspberries, blackberries. Oh, they're so good. And they're good for you. Okay, they're very healthy. I don't eat ice cream. Okay, yeah. Do I have ice cream in my fridge? Yeah, I do. Two different kinds. Yeah, every now and then I eat ice cream. Okay, but I prefer berries, fruits, right? So, oh yeah, cebolla. Okay. Oh, this raw. It's not raw onion. It's grilled onion, but it's like looks like a boiled egg, man. Whole onion. They grill it in the taco stand. I lived in the San Fernando Valley like 10 years ago, 20 years ago, 15 years ago. They have this North Hollywood. Okay, and the west side of this Santa Monica mountain range. I think we talked about this before. Okay, yeah. On top of this mountain range is the famed Mulholland Drive. Okay, director David Lynch, which is one of my favorite, like, kind of avant-garde, artsy, theatrical movie. I love that movie, Mulholland Drive. I mean, the part I didn't like. Why did you have to show this lesbians, man? Ah, come on. But they all ended in misery. Okay, so yeah, that part is correct. Yeah, lesbian marriage, gay marriage, it all ends in misery. Okay, and talk about misery. There's this wonderful Hollywood movie, Kathy Bates, right, as a nurse who rescued this writer, novelist. I think it's in the middle of Colorado or something. Some outback, way outback country. He was driving to his cabin to work on his novel, and this Kathy Bates, he rescued. She rescued him. From a car accident, and he wakes up and there's this Kathy Bates. I'm your number one fan. Oh my god! I love that movie and the story. Oh my goodness, so good, so well written. Ah, it's he lights up his novel to burn it. Oh man, it's so beautifully done. The movie and the actual story. Oh my goodness, it's just back in the days, Hollywood used to produce a lot of good movies. Okay, not too long ago, 1990s, 1980s. I mean, even this Born series, Born Identity. Yeah, that was cool. 'Cause I didn't want to see that movie. This what Matt Damon or something. He went to Harvard. Yeah, he did drop out, but still, I'm an elitist, whatever. So I didn't want to watch that movie. But I was listening to radio back then. I was in California, Los Angeles, right here in San Fernando Valley, NoHo, North Hollywood. Okay, try to sound like Soho, kind of cute. Soho in Manhattan. I've been there too. Okay, I visited Mr. Namjoon Paik's Holy Solomon Gallery, and they were kind enough to show me his actual work studio. Yeah, because I told them, hey, I'm Korean, and Mr. Namjoon Paik is Korean American. Well, so am I. I'm Korean American. So can I see him? And they said, well, he's away, he's on his business trip, whatever. But yeah, we can show you his work studio. And I saw it, and it was fantastic. Okay, I'm a huge fan. I mean, he's number one fan, but he unfortunately passed away. I was so sad when I found out he passed away because I didn't know for years since he passed away. I didn't know, but one day I looked him up in the internet, and he passed. Found out he passed away from old age. He lived fairly long. Okay, I was so sad. Okay, well, life is short, art is long. So yeah, the west side of there's Los Angeles downtown there, Hollywood. There's I think it's 405 or four something highway that connects the two, and there's 101 I guess highway connecting the two, and there on top of this Santa Monica Mountain where you can look down on both sides of the mountain range. Yeah, there are Hollywood big mansions, like very expensive, fancy mansions. Probably they cost like hundreds of $1 million a piece, I guess. And yeah, that's Mulholland Drive. Okay, I drove there too. Okay, just to look at what other mansions, Hollywood mansion, whatever. Yeah, so there's Hollywood, there, Los Angeles downtown, and there's Santa Monica Beach. Okay, yeah, Los Angeles, very interesting town. Yeah, if you go to the east, yeah, you have bigger, even bigger mountains and also desert land. If you go all the way to the east, where on the west, yeah, you have ocean. So you have mountain, desert, mountains, downtown, beach. You have everything. Los Angeles, yeah, it's a fantastic town, tinsel town. And here, this what south east east there is this Universal Studio lot. You know, yeah, big time studio. There's Burbank. Yeah, cool cool stuff. So I woke up, okay, and I read this book about people like me, who's nobody, who's not established but running for president. Okay. Um, I had two interviews so far regarding my presidential candidacy, and they are Californians, both of them. Okay, and I'm very grateful that they interviewed me. Okay, like telephonic interview, like 10 minutes, 15 minutes, because these people are looking for some crazy lunatic, like perhaps like me. So I talked to them, and they realized I'm not that crazy enough. So I think they decided not to put me in their shows. Okay, so I'm reading this book about this candidates, presidential candidates, who's just nobody, just like me. Okay, and I think that's what they're looking for because they live in California, so they want some entertainment. It's their job, and the crazier the better, right? So I talked to them, yeah, and they realized I'm not crazy, so they decided not to put me in their shows because I'm not just interesting enough. Oh yeah, okay, you're not crazy. Yeah, you're kind of boring. Okay, you're too realistic. You're too sane to be on our shows. Uh, well, but I told you, yeah, I've been to Looney Bin in South Korea. So if you think I'm crazy, well, you are not the first one to think that way. You are not alone in that thought. Okay. Oh boy. But yeah, I went to mental institution when I was a teenager in Korea because I ran away from house, school, and back then, I don't know about now, but back then, South Korea doesn't have this shelter system like in America for runaway children. They don't. So If you're gay, if you smoke marijuana, if you run away, if you are transgender, LGBT, yeah, they back then in 1990s, yeah, you're all sent to mental hospital. I'm stating the facts because those are the people I met in this mental hospital. Okay. I met some other people who were running for president in South Korea, and they're nobodies. So yeah, they sent them those presidential candidates to mental hospital. I met them. Okay, I'm telling you the facts. Okay, I'm not making this up. No. Of course, I have to run away from South Korea because I don't want to live in mental institution for the rest of my life. In America, yeah, people like me, like what functional schizophrenic, Mr. Zykiel and Hyde, whatever. But we are functional, right? Functional lunatics. So yeah, I mean, I have my job. It's not like I'm living on disability or anything. Yeah, I got my job. I pay taxes. I pay tax. I pay my bills. Okay. Oh boy. I go to work. But yeah, I have ambition. Okay. So people, my friends, none of them think I'm crazy because they know I'm not. Okay. And they're so kind and generous, my friends. They say, yeah, I'm ambitious. And I am. Okay. And even this Californian, you know, show business people, yeah, they interviewed me and they found it that they realized that I'm not just crazy enough to be in their show. Because the crazier, the better, right? All these lunatics, whatever. But I'm not that. I'm realistic. I'm a realist, and yeah, I do have big ambition. But at the same time, I'm a realist. So yeah, you know what? You are too sane. You are boring. So we're not gonna put you in the show, okay? Because we want some real crazy people here, okay? Running for president. Yeah, I'm running for president, but to me, actually, maybe it's a therapy, okay? Maybe it keeps me from going insane. Maybe it keeps me sane running for president because I'm kind of separating my insanity and sanity. Maybe it's an outlet or ventilation window where I can just pour in all my insanity out so that I stay sane, maybe. Huh? Yeah, it's like negative copium, positive copium, right? Separation of the two. Like all my stress, like, I'm running for president. So yeah, ventilation window, okay, I get all my insanity off the window so that in my house, I'm sane person. Oh boy, it's kind of funny notion, huh? But to me, it's just a hobby. Okay, that's why. What kind of idiot run for president as a hobby, man? What kind of? Maybe I'm the craziest of all. Okay, and perhaps maybe they these Californians they thought I'm crazy, but kind of boring in a boring way. Maybe I'm crazy, but yeah, you know, you're crazy, but you're too boring regardless. So we're not gonna put you in my show. I don't know what they were thinking, but yeah, I think they decided not to put me in their shows. Okay, and that's fine. I was just grateful for the interview opportunity, regardless. It was cool. Okay. Oh, Cebu, yeah, I'm still thinking about this wonderful taco stand. I lived in those Hollywood, this Hispanic neighborhood. This wonderful taco stand, and oh my goodness, I still remember. It just Cebuya and the real Mexican taco, not some Americanized fake taco. No, Mexican real taco, like with lengua, cow brain, whatever, right? Just melts in my mouth. They have what the cilantro and this. Oh my goodness, so good. It was taste of heaven. real taste of heaven. Okay. Whew, yeah. Okay. Let me snap out of that. But I remember wonderful Mexican, authentic. I've been to Mexico too. Okay. Tijuana. Yeah. When I was living in Los Angeles. Yeah, I went to Tijuana sometimes, and they have this seafood cocktail with octopus, pulpa, whatever, and they have this the what coconut. The real coconut, right? Is kind of like fresh coconut, and so they cut the top off and stick the straw, and I was like, oh my goodness, the real coconut milk, man. Oh boy. And after I'm done, yeah, hey, would you give me this flash of coconut? And they did. Oh my goodness, it's so good. Mexico is a fantastic country with very beautiful ladies too, and amazing cuisine and great music, dancing. Mexico is a wonderful. I love Mexico. It's a fantastic country. Okay, yeah. So amazing people, amazing cuisine, amazing culture. Oh, Mexico is a wonderful country. It's a beautiful country too. Beautiful ladies. Oh boy, they're amazing. Okay. But the people that come to America, Mexicans that come to America illegally, yeah, they are not cool people. They have no respect for law. So because many Mexicans, like President Trump said, yeah, they try to come here in a legal fashion because they respect American law. Yeah, then they should be able to come. But so I kind of agree with President Trump on that. Okay, but people who just come here illegally, they have no respect for American law, so they shouldn't be here. Okay, so yeah, I agree with something that President does, Trump does. Okay, or things. Okay. All right. So you know, so it was like 10 minutes, 15-minute interview with those Californians. They were very generous and nice to me. I mean, it was too short period of time, so when I talk to them, yeah, I just talk normally. I'm not crazy. So they realize is I'm just boring to be in their shows. That's fine, okay. But uh, I guess I'm kind of interesting person because it's not just presidential dream that I have. And what the hell am I doing? Infinity algebra, humanology, that I hope one day would replace psychology. And we came up with this transactional demand theory that we hope one day would replace this Alfred Marshall's supply and demand curve in economics, which we have been like forever. Yeah, so I have big ambitions like that. Presidential candidacy is just one of my ambitions that would convince many people to think that I'm really not cracker. Okay. But I didn't tell them all anything about this. Why? Because it was 10 to 15-minute interview. I have a lot of stories to tell, but just didn't have enough time. So, anyways, yeah, whatever. If you think I'm crazy, well, I don't blame you a single bit. Okay, so well, but this is America, okay? I mean, there are people, a guy marrying another guy, like Anderson Cooper, the Poop Cooper, and then there is this lesbian running the show in MSNBC or Rachel Maddow or something, who married a girl and call each other wives. I mean, don't you think that's crazy and stupid? People cover themselves with tattoos and piercings. Yeah, That's America right now. Legalization of marijuana. Don't you think that's crazy? I think that that's insane. Okay? So if you think I'm crazy, well, I think you are crazy too. I think the rest of America is so insane to do this tattoo piercing, gay marriage and shit. Marijuana. Oh my goodness. So if you ask me, I think it's America that's crazy, not me. Whatever, man. Whatever. Okay. Now I'm feeling a little bit better. Okay. This bitter taste of this long nap kind of disappeared. So should we go back to infinite algebra? Maybe a little bit. Okay. So you know. Oh yeah, we had to solve this problem, right? Limit 1/0. Yeah, but L'Hopital's rule came to rescue because I remembered that, yeah, L'Hopital's rule apply only in the situation where it's zero, infinity over infinity or 0/0, that kind of situation. That's when L'Hopital's rule applies. Okay, so in this kind of case, or limit of what, 1/0, 0/1, yeah, that's not infinity over infinity or zero, infinity dot, zero dot, zero dot. Okay, it's not that situation. So yeah, L'Hopital's rule, the precondition of that, it came to rescue us. I guess. Great, thank goodness. Okay. Oh boy. So, a is infinity plus 1 is equal to infinity? So this is like x plus 1 when limit x go to infinity, right? X plus 1, okay? So in this kind of situation, it's like, it's not 0/0 or infinity over infinity, okay? It's not that. So we cannot apply L'Hopital's rule. So then what do we apply? What do we use? Yeah, bigger notation, okay? So it's not a fraction, okay? Fine. Bigger notation of x squared plus 2, yeah, it is equal to bigger notation of x squared. Why? Because 2 is insignificant. So bigger notation is kind of like x go to infinity, okay? When 2 become just too small, and x grows up and up and up, yeah, you can ignore this too, okay? Because it just kind of disappears, relatively speaking, okay? Ah. It's like this, all right? If we really want to do some ratio test kind of things, it's like this, okay? Limit x squared plus 2 is equal to limit x squared 1 plus 2 over x squared, okay? Right? Limit x go to infinity, okay? X go to infinity, okay? So as x go to infinity, yeah, this guy, it disappears, right? Like 2 over infinity, yeah, zero, it zeroes out. Okay? Because limit is very distributive, okay? So yeah, then 1 times x squared, yeah, that's infinity right there, okay? Okay, so that's how it's being explained in a traditional fashion, okay? Good old ways. So the reason why we are doing infinity algebra is to simplify. Let's get rid of all these intermediary steps. Okay, and let's not write this limit x go to infinity. It's just okay. So infinity algebra is just convenient notational convention. It's nothing new. Yeah, there's some new stuff there. We found second L'Hopital's rule. We found absolute infinity as a constant. Okay, so it's we are not just doing some notational convention for convenience sake. We're doing a lot more than that. But big part of it is of infinity algebra is notational ease, efficiency, convenience. Okay, so because we want to be fully backward compatible with this traditional, you know, asymptotic asymptotics of functions, yeah, limit, in calculus. Okay. Okay. Maybe later on we'll talk about like Taylor expansion, something like it. That's really cool. I learned it long time ago, but I kind of re-encountered in Wikipedia navigation something what 1 times e to the 0 over 0 factorial plus, I mean, x to the 0. And then x to the first over 1 factorial plus x to the second over 2 factorial. Something like that, okay? It's something really cool stuff. But we may tackle this Taylor series or not later. Okay, because this is just too much. Okay. We'll tackle this later, okay? Yeah, it's we'll do this later. If that. We may not do this at all. Okay. But to me it's just too much. Okay. We just do the basics first. Okay, Taylor said, oh man, I really don't want to do it. It's just too much. Okay, we'll leave that to you or some other mathematicians. How to connect infinity algebra and Taylor series or infinite series. Okay. Okay. Because we are dealing with enough infinity here. Okay. We don't want to overload our brain with too much infinity. Life is short, my friend. Life is short. Okay. So. Okay. So infinity plus minus some constant, unless they are like absolute infinity, then absolute infinity it observes everything. Okay, even this infinity variable. Okay, is equal to infinity dot get some kind of infinity, and absolute infinity which doesn't have any sign. It's like vertical line, right? Yeah, just like 0, it has no sign. Okay? Plus minus some kind of infinity is equal to, yeah, infinity dot dot. It observes this regular infinity. Okay? Okay? It's like 0, okay? 0 multiplied by or divided by some constant is always what? 0, right? It observes everything. But if 0 plus minus a, it destroys 0. So that's the vulnerable point of 0. How about absolute infinity? Is there any way to make it disappear? Yeah. 1 over absolute infinity, right? Which is absolute 0. Okay? true zero. All right. Yeah. Then infinity disappears. Okay. How about, so you got it? Should I take a picture of this? Maybe. Uh, Let me go grab. We'll take a break, okay? Let me go grab my cell phone. Ugh. Okay. Oh, my cell phone is right here. Hmm. Yeah, I gotta charge my phone, by the way. Boy. Ugh. Ugh. Okay, let's take a break, all right? Because we're gonna think about limit of uh, x plus ln x, okay? We're not sure we can just throw out ln x. Is this equal to limit of x? That'll be our question, okay? Limit x go to infinity, okay? So is this equal to limit of just x? Why don't you think about it, okay? All right, yeah, think about this, okay? So second L'Hopital's rule, first L'Hopital's rule, they both have to be this type of 0 over 0 or infinity over infinity, okay? So we cannot apply L'Hopital's rule, either first or second. No. Okay, so yeah, think about this problem, all right? I just kind of gave it away, right? We can easily convert this guy to something else by factoring it out. So why don't you think about that, okay? All right, we'll take a break. All right, we are back. Let me grab my blanket. Oh boy. Yeah, I'm wearing short pants because kind of it got very hot today. When I was sleeping, I was like, "Oh man, it's like summer." Okay, so let's go over this. Okay, so this is very easy problem. Probably you could just calculate in your head, right, without writing down. But for the people who's not very familiar with this calculus and stuff, we'll spell it out. Okay, so limit of x plus ln x is equal to limit is an operator, a function. Okay, x 1 plus ln x over x, right? Which is equal to, yeah, it's highly distributive operator, okay? Which is equal to infinity multiplied by, now we are distributing this inside, okay? Limit of 1 plus limit of ln x over x. Now we can use L'Hopital's rule here. And we can also use the second L'Hopital's theorem too. Okay, because it's infinity over infinity situation. Okay, so let's do that. Is equal to, okay, so is equal to what? You have infinity times limit 1 is just 1, right? So you have infinity plus infinity times limit, yeah, we can use the second L'Hopital theorem, okay? So it's e to the x, okay, inverse function, ln x inverse is e to the x. It switched upstairs and downstairs. And yeah, inverse of x is just x, okay? Which is what? Zero, okay? Oh boy. Now, so we have a situation here, okay? You have infinity plus infinity multiplied by, yeah, we use by using the first L'Hopital theorem is this is equal to 1 over e to the x, right? You differentiate both sides, right? And then so it's e to the infinity over 1, okay? And this is equal to, this is 0 dot. It's some kind of infinitesimality, okay? But because e to the infinity is a lot faster than just infinity, okay? Uh, we didn't have to quite use the L'Hopital's rule here because ln x differentiated is 1 over x, right? So yeah, we can just use first L'Hopital's rule. You differentiate x, that's 1, so it's just 1 over x. We could have done that, okay? Yeah, but it doesn't really matter, all right? I think ln x differentiated is it 1 over x? That's what I remember. I gotta get back my cell phone so that I look up what's the differentiation of ln x. I think it's 1 over x. derivative of ln x. I think it's 1 over x. That's what I remember. Yeah, it's 1 over x. Okay. Derivative of ln x is 1 over x. Okay, so it's by using the first L'Hopital's rule, ln x over x becomes what? 1 over x, because this x guy you differentiated becomes 1. Okay, so yeah, we could have done that way, but it's more interesting to look at this way, because now you have e to the infinity and infinity. They are the first order infinity, Yeah, that's, you divided by that is equal to infinity plus 0 dot, some kind of infinitesimality here, okay? And which is equal to infinity, okay? Okay? So yeah, we are kind of mixing the traditional limit method and our brand new infinity algebra, okay? We're kind of bridging the gap here by using both of them, all right? So it's instructional, all right? By the way, okay, you got it? Yeah, it's easy, right? By now, we are very familiar with infinity algebra, so yeah, it's fun stuff. Very neat. Okay. So 1 plus 0 dot, we can call it as 1 dot. Something like that, okay? Whatever. It's like 1.00001 and it keeps on going like forever, okay? And how about square root of 2? Well, 1.412, something like that, right? Something like that. 1.14414, something like that. But it doesn't go toward infinity, okay? Because square root of 2 is always less than 1.5. It doesn't grow like forever. It kind of stays there, kind of like vibrating, okay? And it's always more than 1.4, okay? So yeah, between 1.4 and 1.5, it kind of vibrate a little bit, okay? Okay, like you have 1.4, right? And then you have 1.5, and square root of 2 is kind of like vibrate in between, something like that, okay? So yeah, it's finite. It doesn't grow. Let's say 1.4 plus 0 dot, okay? It's not that this is not equal to square root of 2. That's the point I'm trying to make. Because 0 dot, it gets closer and closer and closer to 1.4. Okay? It approaches 1.4 forever. It's still going. It's a variable. This is not a constant. Okay? But this guy is a constant. Okay? It's kind of strange kind of constant. They call it irrational number because there's no fixed pattern. Okay. I just want to distinguish between the two. That's all. Okay. What are some other irrational numbers? Yeah, sine, cosine, those trigonometric numbers. They are irrational numbers too. Okay, because what is sine 45 degree? Well, curiously enough, is actually expressed in terms of this radical. Okay, from what I remember, is 1 over square root of 2. Okay, something like that. Which is equal to square root of 2 over 2. Okay, so it's like what? 0.7 blah 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 blah. Okay. Okay. And talking in terms of radicals, we found something curious. Okay, something that's probably akin to this Galois theory, group theory, where we had function is y is equal to x plus square root of x, right? Probably the inverse function, you have x is equal to y plus square root of y. Now, can we solve this equation in terms of x? So let's say there's fx, right? This will be inverse of fx. Okay? And probably we cannot express this inverse function of this guy. Probably we cannot express this in terms of algebraic operation. Okay? Just like the solution, general solution of polynomial of fifth degree and up is not expressible in general in algebraic terms. Okay, probably something akin to that. We probably it's not too hard to prove this. Okay, probably it's not too hard to prove this. Or not. Maybe I should study Galois theory, but I don't really want to. If do you already know Galois theory, yeah, then why don't you apply that to this? Okay. Probably impossible. Yeah, but Galois, maybe if I have time left, maybe after I retire or something, maybe I study Galois theory. But for now, I don't quite feel like studying that. Okay. It's just too much. Okay. And I'd rather just move on. Okay, so yeah, probably it's not. Probably we cannot solve this in a nice and neat algebraic term. Okay. Or maybe you can. I don't know. All right, but I don't know how to. All right. How about this? Something simpler. Y is equal to y squared. X is equal to y squared plus y. Well, okay, maybe you can solve this in terms of y then, because it's just by using the what? By using the traditional what? Quadratic equation. Then this should be solvable then. Okay, okay, well, I was wrong. I'm like, what an idiot. 2a minus b plus minus square root of b squared minus 4ac. There we go. Okay, let's verify. 4y squared is equal to 1 plus minus square root of, squaring both sides, okay? 2 times 1 plus 4x plus 1 plus 4x, okay? My goodness, it's getting messy very quick. Is this equivalent to that? I don't know. Okay, so 4y squared minus 4x minus 2 is equal to plus minus 2 times 1 plus 4x, okay? Square root of that. So 2y squared minus 2x minus 1 squared is equal to 4 times 1 plus 4x. My goodness. 4y squared, y to the fourth. Do you want to do this? I don't want to. Oh my goodness, it's getting really messy. Did I make any mistake here? You have 2a minus b plus minus b squared minus 4ac, you know. It has to be this. Four y squared 1 well, minus plus 2 times that is equal, and this guy squared, so that's that, minus 4x minus 2 that is divided by 2. Okay, I don't even know why we are doing this, just for fun. Okay, because we got nothing else to do. We'll just expand this. Okay, minus 4xy squared minus 4y squared plus 4x plus, yeah, that's that, is equal to 4 plus 16x. I don't know where we're going with this, man. My goodness. All I want is to get back to this guy. Okay? Wait a minute, what did I just do? I squared it, huh? Why did you have to square it? All you gotta do is plug this in and make sure it works. Whatever. Yeah, I'm dumb and stupid. Okay, so let's just plug this in. Okay, and then you have what? 4 1 plus minus 2 times 1 plus 4x plus 1 plus 4x. Okay, we got that, plus y plus minus 1 plus minus square root of 1 plus 4x. Is it minus plus? Let's see. You're squaring it, right? 2 times that, yeah. Minus plus. Yeah, that's ordering kind of matters here, so. Okay, so minus x is equal to what? So this minus plus and plus minus term, they cancel out, okay? Because it's 2 over 4, all right? Now, what else do we have? So this guy is equal to, and 1 here, that's 1 over 2. So minus 1 over 2, they cancel. So this term entirely disappears. Now, the only thing that we have left is 4x over 4, which is x, and x, they cancel out. It becomes 0. So yeah, this is the correct solution. Okay? Now, okay, then it's easy now. Okay? We're trying to find inverse function, okay? So yeah, I was wrong. It was solvable. It is a solvable function, okay? So you have what? Y is equal to x plus square root of x, right? We'll call, and to find the inverse, you have x is equal to You switch y and x, okay? That's how you find inverse function. Okay? So, we call square root of y as m, okay? So, y is equal to m squared, okay? And we'll call this then this problem becomes x plus m squared plus m, okay? Which is same as this guy. We are just calling m instead of y, alright? So let's say this is m, which is square root of y, okay? All you gotta do is just square it. So y is equal to minus 1 plus minus square root of 1 plus 4x squared, okay? Yeah, it's not very pretty function, okay? You got it? Yeah, and if this is like what? This guy plus this guy, so 2 plus square root of 1 plus, oh no, 2 plus 4x plus minus 2 times 1 plus 4x is equal to 1 plus 2x plus minus square root of 1 plus 4x over 2. Okay, so that's, I'm not going to even zoom it in for you because this is ugly. Okay, it's nothing pretty or worthwhile to look at really. Okay, so yeah, so it is possible to solve this guy. This is just quadratic equation variation there. All right, so yeah, that's the inverse function of this. Okay, this guy is the inverse function of that. Okay, I mean, but we didn't quite have to do that because we're trying to find out L'Hopital's theorem of this guy over 1, but we realized later on L'Hopital's theorem doesn't quite apply because it's not infinity over infinity, it's infinity over 1 type. But we did it for fun, okay? So, but in this kind of situation, yeah, you can always transform that question into infinity over infinity type. Okay, why? I show you. So so that you can apply L'Hopital's rule. Limit x plus square root of x is equal to limit x 1 plus square root of x over x, right? Now you have infinity over infinity. Okay, of course, you know, you don't even have to do that. You don't even have to use L'Hopital's theorem. Okay, this is 1 plus what? Square root of x, 1 over square root of x. So if x going to infinity, this guy dies out, becomes 0. So it's just become, you know, infinity to the first. Right? Okay? Because this is same as limit, this whole thing is under this limit, okay? Limit x multiplied by limit 1 plus square root of x up downstairs, okay? So this is go to infinity multiplied by 1 plus 0 dot, right? Which is 1. Oh, no, this is 1 dot, okay? Okay, so infinity plus infinity multiplied by 0 dot. Okay. Well, yeah, okay. So, but here you have infinity over what? Square root of infinity, right? And by using second L'Hopital's rule, it'd be like this. Infinity and infinity squared. Inverse function of square root is squared, right? Which is equal to infinity. Okay. Okay. Then we have what? Infinity plus infinity, which is equal to 2 times infinity. Really? It's not quite the result we were expecting. Okay. It's not quite the result we were expecting, because we were expecting that this guy gets absorbed. Did we make any error somewhere? Oh boy. So this is y is equal to square root of x, and I see. But yeah, I guess I made a mistake here because actually not. So inverse of that is this is y is equal to x squared. Okay, half of that, but we don't care about the other half. All right, because x is positive, it goes to positive infinity. All right, so this has to be true. Just my goodness. Maybe it, I don't know, like something's quite not quite making sense. Okay, so it's either we made some mistake or our system of infinite algebra is there's some error in there. X go to infinity. Okay, x plus square root of x. Okay, is equal to limit x 1. Oh, maybe I made some calculation mistake then, or not. Ugh. Okay. And limit of x maybe I have to take a look at how they proved L'Hopital's theorem, because they may have glossed over something. Okay, because the traditional this limit algebra, it's kind of it gloss over many things. Okay, they don't quite differentiate things that we infinity algebraists differentiate. Okay, traditional limit algebra is a lot simpler than what we do here. Okay, so I have to look at how they prove L'Hopital's theorem, because it looks like L'Hopital's theorem or the second L'Hopital's rule. I guess there's something not quite exactly correct. Okay, I think they're glossing over something. Equalize something that we tend to differentiate in infinite algebra. Okay, so uh, yeah. Well, let's take a look. We'll take a break soon, okay? But let me take a look at the L'Hopital's theorem, how they proved it, okay? A45, Appendix 45. How did they prove it? Well, I gotta go back to Cauchy's mean value theorem, dude. A lot of backtracking here. Oh boy. Mean value theorem. I gotta. Okay. 288. Mm-hmm. Okay. Well, the problem is this, okay? Cauchy, Lagrange, whatever. This whole thing, okay, is based on this rather incorrect notion where square root of infinity is equal to infinity, okay? If we just say square root of infinity is equal to infinity, then yeah, this makes sense. Because they are all just one infinity. But in our infinite algebra, not so, because we want to differentiate many different kinds of infinities. Is it fast infinity or slow infinity? We want to differentiate that. We want to distinguish between two different kinds of infinities. But uh, this whole thing, L'Hopital's rule, whatnot, the whole history of calculus, okay, they treated these two things as the same thing. Okay, so if we do treat this the same thing, then this whole thing makes sense. But in infinite algebra, we want to distinguish the two. All right, so perhaps we have to modify L'Hopital's rule, tweak it a little bit. Okay, I mean, look, the way they prove L'Hopital's rule, it's not that difficult at all. It's just mean value theorem. Okay. Uh, let's take a step back, okay, and go over the mean value theorem real quick. All right. well, mean value theorem is this. Okay, you have A, B, FA, FB. Okay, and there's some C here between A and B, and here you have the slope F prime C, and what mean value theorem is saying, F prime C, there exists C such that is equal to this straight line. Okay, the slope of these two things are the same, right? There exists the C between A and B such that FB minus FA is equal to something like that. Okay, so that's mean value theorem. And Cauchy's mean value theorem is just you're adding one more function. Okay, you have G prime C is equal to G B minus G of A and B minus A. So you just divide by these two things. Okay, assuming G prime C is not zero. All right, then F prime C over G prime C is equal to F B minus FA G B minus G A. Okay, and originally the L'Hopital's rule is about x approaching this constant A, but later on from there it's easy to prove L'Hopital's rule still holds when x go to infinity. Okay, so from here to jump to L'Hopital's rule, it's not too easy. It's not too difficult either, but um, Oh boy, I'm sorry. I've been showing this whole time. I'm showing my ugly bald spot. I'm sorry. It's weekend, so I don't do my hair. I'm sorry. Ah, well, how about this? Yeah, sorry to show my bald spot. Okay, I know it's ugly. What can I do? All right. Oh boy. Hmm. Okay, well, let's move on. All right. So basically, it's a mathematical sleight of hand. That's how typically people with good mathematical proof skill, yeah, they do a lot of sleight of hand here. So here we're gonna substitute some characters. Okay, so uh, f prime y g prime y is equal to f um, no. So c is y and b is x. Okay, fx minus fa gx minus ga. Okay, and a y x. Okay, so y is the one between there. Some some number between a and x. Okay, and and they're doing something very strange. They define large fx where large fx of a is equal to 0. It kind of almost look like cheating to me, but yeah, they do this strange thing, and I mean it makes sense. It looks weird, but it doesn't contain any logical error, so I guess yeah, that's fine. But yeah, the way they prove this L'Hopital theorem, I'm looking at this book, but it's in the online, it's on the web. Okay, so if you're curious how they go about proving this, yeah, go for it. Okay, but yeah. Yeah, when x approaches a, yeah, y approaches a too. So they're saying, uh, okay, so they define fx where fx is f large fa becomes zero. Okay, that's the definition of large fx, and then um, so this becomes fx over gx, and okay, so here, oh boy. Mm, oh, I'm sorry. My pulse part again. Um. Okay. Ah, yeah, yeah. I understand this L'Hopital's rule. How they proved it. Okay, they just define some artificial function, whatever. Kind of bifurcating function like f large f of x is equal to small fx if a is x is not equal to a, and 0 if x is equal to a. So very clever, okay, clever manipulation so that this f of a kind of disappears. Yeah. And then this whole thing becomes what? Yeah, then they have large f prime y, large. Yeah, I understand what they're saying, but yeah, I didn't quite like the way they proved this. Okay, but I'm not gonna try to prove L'Hopital's rule in some other way. Well, maybe there are some other way to prove it, but yeah, whatever. So yeah, this infinity algebra, it's not quite working. Okay, it's not quite working because oof, limit x plus square root of x. Okay, that's the problem we are having here. And which is equivalent to another problem where limit of x plus x squared plus x, okay? In bigger notation, this is o to the x squared, okay? So this guy kind of disappears, you know. But if we apply L'Hopital's rule, we encounter some problem, okay? So let's say we do factor out like 1 plus 1 over x, right? Which becomes what, infinity squared plus limit infinity squared over infinity, okay? So we should be able to apply L'Hopital's rule, which is equal to, you differentiate upstairs 2 times infinity. So infinity squared plus over 1. Okay, it's not too bad. Well, the problem is we try to use the second L'Hopital's rule, okay, where uh, limit f over g is equal to limit f inverse g inverse. Okay, so that's the second L'Hopital's rule we proved, which is very easy to prove, you know, using the inverse function theorem and L'Hopital's rule combined. Then we have that. But inverse function theorem, maybe there's some kind of precondition to that theorem. Maybe that's where I kind of got screwed. Okay, so inverse functions, you know, is there any condition to that inverse function theorem for it to be true? Maybe I missed something in the inverse function theorem. Oh boy. I guess I kind of misstated the inverse function theorem. Okay, so may have made some mistake. Okay, well that happens. Oh boy. Maybe I misstated the inverse function theorem because I thought it's like f is equal to f inverse over 1. That's the way I understood inverse function theorem. Okay? Maybe that's not correct. I don't know. We'll take a look. Okay? So, maybe if I was incorrect, then second L'Hopital's rule where we have to modify that. Okay? Because my understanding of inverse function theorem is this, but maybe it's incorrect. It's like dy dx, you know. Go 1 over dx dy, something like that. Okay, so something like this. Okay. So let's see if it's correct. Okay, how about e to the x prime is it equal to what's inverse of e to the ln x, right? Ln x prime. No, that's incorrect because ln x prime is equal to what? 1 over x. This becomes x, and this not is not equal to e to the x. So yeah. Okay, so my understanding of inverse function was incorrect. I guess. I'm sorry. Then what's the correct statement of inverse function? So I guess second L'Hopital's rule. I'm sorry. I guess it was wrong. Okay, because my my bad. Okay, I'm sorry. I'm ashamed. Okay. Um, then what is the correct statement of inverse function theorem? I'm so sorry, but we all make mistakes, right? So yeah, sorry about the mistake. Okay. Yeah. Well. Inverse function theorem. Let's see. Well, let's put this cap back on. Cause it's gonna take a while. Oh boy. They're doing all this n-dimensional stuff, multivariate environment. I'm not interested in this Jacobian and all that stuff. I just wanted one variable, single variable. Just one variable. Single variable. Okay, so looks like the correct statement of inverse function is this. So yeah, I erred. Okay, I'm sorry. So we'll have to modify the second L'Hopital's rule. Okay, so I'm sorry, it's my bad. Okay, so here we go. Okay, so this is not that, but f prime is equal to um, 1 over. It's a little bit involved. Okay, f inverse prime my goodness. prime, something like that. Okay, so that's correct way of saying it. Which is, oh my goodness, this it's too bulky and too complex. Boy, I'm not sure if this is any useful to us. How on earth would you? Okay, for example, e to the x, okay, prime is equal to what? ln e to the x prime over 1. Let's see if it is correct. ln e to the x is just x, right? Did I make another mistake? My goodness. I don't know. Ooh. Oh well, it is actually prime goes here. Okay. All right. ln x prime, that's 1 over x. So ln x prime, that's 1 over x. And inside of x, you have e to the x. Okay, okay. Okay, then it makes sense. Okay, so okay, okay. All right, so we we got this. So then let's come up with a correct second L'Hopital's rule. Okay, so correct inverse function theorem is this. Okay, it's a little bit ugly. You have f inverse to the prime, and then you apply instead of my goodness, what a mess. Yeah, you apply this. Is a composite function. Okay, something like that. Okay, composite function. All right. Fx, it becomes a variable for this function. Okay, that's what this means. So, let's derive the second L'Hopital's rule. Okay. At this point, we are not even sure there will be a second L'Hopital's rule because this whole time we've made it's me. I made mistake. Okay, so that's limit what f prime g prime, which is equal to f inverse prime applied to fx. Okay. Yeah, we can do this. All right. Because I don't like this circle symbol. So f and fx. We'll wrap this whole thing prime. Okay. Well, limit of that. Same way, g minus 1 inverse gx, the whole thing prime. Okay. So applying to e to the x. Okay, e to the x prime is equal to what? F inverse, which is ln x and ln e to the x. Yeah, I guess the this prime operator actually matters. Okay, so yeah, it should come first. Oh boy, what a mess. No wonder nobody wanted to do this because it just gets very messy. Okay, you have to differentiate first. Okay, and then you can plug in the fx, but not the other way. You cannot plug in the fx first and then do the differentiation. So ordering actually matters. Okay. Okay. I mean gx fx. Okay. Okay. Well. Well, we gotta make some examples to get used to these things. Okay. Before we go to second L'Hopital's theorem, let's do some exercise with this inverse theorem rule. Okay. So you have e to the x prime is equal to what's the inverse function? ln x. And what is differentiation of that inverse function? 1 over x. Okay. So you have ln x, but instead of x, you put in the fx, which is ln e to the x. Okay. And if you differentiate this guy later, then it starts making sense because ln e to the x is x goes out, so it is just x. So x prime. So yeah, so ordering of differentiation and inversing of function, it actually matters. You have to inverse, calculate the inverse function first, and then you should plug in the fx. Okay, so ln inverse of ln logarithm is 1 over something. Okay, so and then you plug in e to the x. Okay, and then you have 1 over, right? So that's e to the x. Okay, which makes sense. Yeah, e to the x is just that. Okay. Whew. I mean, is there any benefit of using this then? Because the whole reason when we wanted to introduce the second L'Hopital's rule is that sometimes inverse function is simpler, but as you can see, we are not cut because we want to get rid of the real function. We want to substitute inverse function because sometimes inverse function is simpler, right? But we are not quite getting rid of this fx because we still have to use this fx. Then what's the point of using the second L'Hopital's rule? Because we are not getting rid of the fx. Fx still persists. It gets inside of this f inverse where after differentiating it. So I guess there's no such thing as second L'Hopital's rule then. I'm sorry, I failed you. But I tried. I'm sorry. But that's fine. That's not the end of the world. It was hugely disappointing for me. But well, at least I corrected my error. Okay, I'm sorry. Um, is there any value in this? Trying to. I'm wondering. Hmm. Let's think about when fx is x squared. Okay, so f is equal to x squared. Okay, so inverse function of fx is equal to what? Square root of x, right? Well, let's say this is f and this is f inverse. Okay, so we don't quite want to deal with square root of x because differentiating that is not pretty. Okay, so f prime is equal to inverse function of that, that's x squared. Okay, so you differentiate x squared, so it's 2 times x. Okay, but instead of using x, we put the this this guy here, square root. Okay, so I guess in a way, inverse function theorem is somewhat easier way to differentiate this ugly thing, maybe. Okay. Okay. But we still don't want to quite give up on this second L'Hopital's rule because I think it could be something very powerful. So let's not give it up yet. All right. Um, okay. Limit of, because the original motivation was this, like ln x over square root of x, um, because we don't want to deal with all the fraction and stuff, right? But our second L'Hopital's rule, it was incorrect. Okay. So we want to correct that error. Okay. Uh, okay. So this becomes to ln x. You inverse that e to the x. You differentiate e to the x, e to the x, and you plug in this original function. Okay. E to the ln x. Now square root of x. Okay. You inverse x squared. Differentiate 2x. And instead of that, instead of x, you put the original function, which is 2 to the infinity. I mean 2 square root x. Okay. Now, this is equal to x 2 times square root of x. Okay. Limit of that. Okay. Which is equal to 2 over square root of x. Limit of that. Okay. So yeah, it goes to infinity. Well, that doesn't sound quite right. That doesn't quite sound right. Man, what a mess. What a mess. Oh, wait a minute. We have to differentiate this, huh? Oh, okay. Okay. Well, we are just getting rid of this intermediary stuff. All right. So f is, you have prime here and prime. Yeah. So we can get rid of this intermediary. Okay. So f inverse e to the x, and you differentiate that, that's still e to the x, and you plug in the original function, which is ln x. Okay. Now g to the minus 1 square root of x. Okay. So inverse function x to x squared, and then you differentiate. Yeah, that's 2 times x, and you plug in the original one, 2 times square root of x. Okay. And e to the ln x, that's just x, right? So this is x go to infinity, 1 over infinity. Yeah, that's some kind of 0. So are we saying, yeah, actually it makes sense. I'm sorry, yeah, I was confused. This guy is supposed to be a lot bigger because ln x is inverse function of e to the x, so it is extremely small thing. Okay. And this guy, square root of x. Okay. So yeah, original intuition is that e to the x, that's a lot bigger than y is equal to x squared. Okay. Just like because of that, ln x should be smaller than square root of x because they're inverse functions. It's a mirror image thing. Okay. Yeah. So this is correct, and I guess we solved that problem then. Okay. Um, so second L'Hopital's rule is this. All right. I think it is useful. Why? Because in a way, maybe it was not as simple as we thought it would be. Because, but I think it is. It could be useful. Okay. Because I don't want to differentiate square root of x. Okay. Like x to the 1/2, you subtract that. Oh my goodness, no, no, I'd rather not. Okay, I'd rather find the inverse function of this and then plug in the original function. Okay, so that's this. All right, you find inverse and then you differentiate. Okay, you find an inverse, which is e to the x, and you differentiate, which is also e to the x, and then you plug in the original function. That way, you are bypassing the need to differentiate the original function. You are differentiating inverse function instead. Yeah, you're not getting rid of original function, but at least you save the labor of differentiating the original function. If it happened to be somewhat very messy thing, okay, like arctangent or arcsine, arccosine. To differentiate those functions, it's I don't even know. I have to look it up. What's the differentiation of arc cosine? What's the derivative of arcsine? Maybe it's not too bad. I don't know. All right. Inverse trigonometric function arcsine. Derivative of arcsine, sine minus 1, sine inverse, is 1 over square root of 1 minus x squared. Okay, so it's not that pretty. Okay. Okay. So yeah, this is second L'Hopital's rule. All right. Yeah, it's not as pretty as we want it to be, but this is correct. So we got it. Yeah, second L'Hopital's rule, we got it. Okay, so you inverse a function, okay, and then you find the derivative, and then you plug in. Okay. That way, you're bypassing the need to find derivative of this f and g. If f and g is very difficult to differentiate, yeah, you can bypass it by using L'Hopital's second. Okay. We got it. Finally. Okay, so if inverse of this original function is a lot easier to differentiate, yeah, then the second L'Hopital's rule is very useful. Okay, it's not as pretty as we want it to be, but still, it's a lot better because in case where like ln x or square root of x, whatever, okay, if it's kind of unwieldy to differentiate, then yeah, you use the second L'Hopital's rule instead, because if it's inverse, if their inverse functions are easier to differentiate, then yeah, the second L'Hopital's rule will be very useful. like in here, okay, like or some other cases, okay. Here is not too bad, right? Yeah. So yeah, unfortunately, we are not quite getting rid of these original ugly functions, but at least we don't have to differentiate them directly. We're going to differentiate the inverse function thereof. So it's a little bit easier. Maybe not as dramatically easier than we thought it would be. Okay, so because this original function still persists, right? Like in this example, okay, we got rid of, at least we got rid of the ln x. This time I'm going to zoom it in for you, okay, because it's a lot. And yeah, okay. I'm not sure if you want to see this at all, but there it is. And I'm going to take a picture of this. I know it's ugly. It's such an ugly baby. But we got it. We got it correctly. All right. So it took a long time. And I mean, even professional mathematicians, they make mistakes. Like when this professor in Britain, university, he proved the Fermat's last theorem. He did make a mistake, but he corrected it. So it was now it's accepted valid proof. Okay, boy. I have to make two different shots because too many things in the board. Okay, well, we got it. Okay, so pat on the back. Sorry I screwed up, but at least I corrected it. Okay, and we take a break and we get back to our original, the infinite algebra. Okay. Okay. Now we got the rule correct. So, all right. Thank you for being patient. Thank you. getting chilly here, so I'm sorry to have misled you, but so we'll go back to infinite algebra. Now we fixed the problem. Okay. Oh, it took us a long while. Took me a long while. I'm sorry. You know, being such an amateur mathematician. Okay. Inverse function theorem, dude. Ooh. Now, let's do this. Limit. Time to buy a new pen. I'm gonna turn on the other hero. It's getting chilly. Okay. We all make mistakes. Let's not be too harsh on ourselves. It's okay as long as we correct the mistake, okay? So, boy. Boy. Kind of feel kind of really guilty here, but we all make mistakes, alright? So let's get over it. And I'm gonna have some drinks because we got it, okay? We corrected our mistakes, so it's my mistake, okay? I corrected it, so my bad, okay? So let's move on. Please forgive me, alright? Okay, so let's get back. I used a lot of black pens, so let's do green, blue. It's running out too. Limit ln x over x, okay? Okay. Okay, we just do traditional L'Hopital's rule, okay? Is equal to limit of what? 1 over x, right? You differentiate ln x, it becomes 1 over x. Differentiate x, it becomes 1. So it's 1 over infinity, which is 0 to the first. Okay? Which is 1 over infinity to the first. Okay? Start looking like a devil, man. I'm sorry. So that you can see a little bit better. Alright? So I have to move right here. Okay, so and let's apply the second L'Hopital's rule, shall we? This is equal to. I know it will be more difficult, so there's no necessity here. Okay, but just for an exercise. Okay, so you have e to the x, and you differentiate. You inverse that e to the x, and you differentiate, which is e to the x. Okay. And you plug in, so e to the ln x becomes just x. Now, if this guy go upstairs, so it's and you inverse that, that's just x. Differentiate x 1. So yeah, that's that. So now it starts to make sense. Okay, same thing. Second L'Hopital's rule, yeah, maybe it's totally useless. Maybe that's why nobody bothered to discover it. But I do believe it has some values. Okay, so yeah, discovering useless mathematical formula and shit. Oh, what the hell am I doing? Oh boy, it's a hobby, useless hobby. I mean, just like video gaming. I mean, if you, I guess, at least in video game, maybe what I'm doing is worse than video gaming. Because if you are very good at video gaming, yeah, I guess you can make money off of it. Maybe some video game company hires you, and maybe they would pay you or some competition, and you get international award, perhaps, by the granted by the video game company like Microsoft, Xbox, and whatnot. I don't know. Okay. All right. Just to prove point, when how did they prove limit sine x over x when x go to 0? How did they prove that sine x? Well, I guess it's 0 over 0 type, right? So is what? Limit, you differentiate that in cosine x. You differentiate that 1, x go to 0. Yeah, this is cosine 0 is what? 1. Okay, so yeah, it's just first L'Hopital's rule, right? And how about limit arcsine x over x? What is arcsine? Okay, so it goes like that. Okay, so that they are symmetric in terms of y is equal to x. Okay. Now, if you are trying to use L'Hopital's rule, it gets very messy because arcsine, you differentiate that, is like square root of 1 over square root of 1 plus x, 1 over square root of 1 plus x squared. Okay, you don't quite want to go down that road. Or maybe it's not too bad. Okay, let's do it. Maybe it's not that bad, huh? 1 over what? Square root of 1 plus x squared. Actually, in this case, it's a lot easier than, which is 1, right? Okay. But just for fun, okay, let's apply second L'Hopital's rule. Okay, this is equal to. All right, we'll do x first. X go upstairs, but we find inverse, which is x, and then we differentiate, which is 1. Okay, now we inverse this guy, becomes sine x. Okay, and then sine x you differentiate, cosine x. Okay, then you plug in the original function. Cosine of sine minus x, my goodness, it's a lot worse. Ah! Okay, I'm sorry. I guess second L'Hopital's rule, maybe it's not that useful, okay? Oh boy. Maybe that's why nobody bothered to put it in the mathematical texts like calculus book, whatnot. But we found it, okay? At least we found an equation, all right? But it's not very useful. Probably that's why it's not in calculus textbooks. Okay, I'm sorry. Hmm. Oh well. We tried. I mean, I tried. Okay, yeah, whatever. I mean, x go to 0. Well, it's this, okay? What? So, x go to 0, okay? So, sine, arc sine 0 is what? What is the value of sine function that makes sine x 0? Yeah, 0, right? So, cosine 0, this is equal to limit cosine 0, 1 over cosine 0, which is 1. So, maybe it's not as bad, okay? I want to see derivative of arc cosine and arc tangent. Okay. I want to see it. Because I want to find an example that where this our second L'Hopital's rule could be somewhat useful. Okay, so maybe it is useful. I don't know. Okay. Whatever. You know what? Let's get over it. Okay. Ah, okay. Well, you have hyperbolic function. Okay, hyperbolic function. This potential candidate because we do hyperbolic function. Okay, it's easy. It's hyperbolic function is this. Okay, it's called sine hx. All right, hyperbolic hyperbolic function. Sine hx is defined as e to the x plus e to the minus x over 2. All right, it's just definition. All right, hyperbolic sine x. Okay. So when x go to infinity, yeah, it goes to infinity because e to the minus x becomes 0, e to the x become e to the infinity which is a kind of infinity, okay? So, and hyperbolic function of inverse of that is this ln x plus square root of x squared plus 1, okay? So, and interestingly enough, hyperbolic sine x inverse, and you differentiate that, and it's not too bad. It's square root of 1 plus x squared. It goes downstairs. So it looks very similar to sine x inverse. Okay, sine inverse x, arc sine x. Okay, prime is square root of 1 minus x squared over 1 over that. Okay, it kind of looks similar, which is very cool. Because they defined this hyperbolic sine x in a very random looking fashion. Why the hell do you do that? X, e to the x and e to the minus, you add them up and divide by 2. Where does this come from? I don't know. But from what I remember, I'm sorry, I made a mistake. Minus. Okay. Yeah, cosine hyperbolic is plus. Okay. Sorry. Making a lot of mistakes. So from the way I remember it is cosine hyperbolic is plus. Okay. It came from this tension bridge. You have this long cable. You're hanging in two pillars. So this low hanging tension bridge or any string. Okay, so they came up with a differential equation. What would be the curve of this tension? The string hanging, loosely hanging. What would be equation for that? So they came up with a differential equation and they solved it. And this hyperbolic cosine x is I think the solution to that differential equation. That's what I remember. Okay. Why did they call it hyperbolic cosine, hyperbolic sine? I don't know. All right, because it's not like this traditional trigonometric oscillation. No, it's more exponential function. Why do they make analogy of this cosine and sine? I don't know. All right, but yeah. The hyperbolic function equalities, they are very analogous to trigonometric, just like we see here. Yeah, there's some symmetry going on here. So yeah, I guess it's smart to say it's kind of look like sine and cosine. All right. Yeah, it's very smart. So the second L'Hopital theorem, all right, it's useful when let's state that again. Okay. Limit f over g is equal to limit f inverse prime, and then you plug in the original f, x, okay? They go downstairs. Then g, you find the inverse, and you differentiate, and you plug in the original gx, okay? So, and also intermediary step, of course, is f prime, g prime, right? So motivation is this. If you hate to find the differentiation of f and g, you can bypass differentiating f and g directly. If, for both f and g, if finding the derivative of its inverse functions, if differentiating their inverse functions are easier than differentiating f and g directly, then yeah, the second L'Hopital's theorem works very well. All right? If f and g, you have two functions, right? If differentiating their inverse functions is a lot easier, then it will help, because we don't have to differentiate f and g. Instead, if f inverse, g inverse is a lot easier to differentiate, yeah, then this will prove to be very useful, because we are bypassing differentiating f and g directly. But we are not still getting rid of f and g though, okay? Maybe there's no point of doing this, okay? Maybe there's no point. Because the whole point of L'Hopital's rule is to break down functions by differentiating it again and again and again, or by integrating it again and again, if that's a lot easier to find this ratio of f and g, okay? I'm trying to come up with an example where this second L'Hopital's rule would be very useful. I'm not quite getting it though. Sorry. But let's take a look, all right? Let's take a look. Okay? As x goes to infinity, we know this guy goes to infinity. ln x plus square root of x squared plus 1. Yeah, it will go to infinity, right? I'm kind of excited to do this. I mean, for example, limit hyperbolic sine x over x, what would it be? It's not very obvious, you know. Probably 0, right? Because you have ln x and ln square, well, square root of x squared plus 1 is kind of like x, right? 1, we can ignore that. So it's like ln 2 times x, okay? Yeah, we already know ln x is very slow function because e to the x is very fast. Okay, and the ln x is inverse function of that. It's like 1 over, kind of, okay? Inverse function is kind of like inverse of that, 1 over fx. Kind of. That's intuition behind they use this f minus 1 of x. That's inverse function, okay? Because inverse circle fx is equal to ix, which is an identity, which is y is equal to x, okay? Okay? So that's the intuition behind that. It's kind of like, it kind of is this, as if this guy is multiplication and this guy is inverse to each other in terms of multiplication, and this ix is like 1. Okay, so that's the intuition behind that, right? I mean, would you like to differentiate this thing? Which isn't too bad, but I don't want to differentiate this. No, I'd rather use the second L'Hopital's rule, okay? So let's try that, okay? This is equal to, okay, find inverse function of that, which is what? Hyperbolic x, okay? So, and it goes downstairs, right? So you have 2 over e to the something minus e to the something. You need to differentiate that, okay? E to the minus something. So you first you first inverse it and then you differentiate it, okay? And x go upstairs, you inverse that x, and it's x, and well, limit of that, and then you differentiate, it becomes 1. So yeah, you can know that, okay? So that becomes e to the something differentiated by e to the something, that's still, that becomes e to the minus flow out there, so e to the what? Original thing. Sine inverse hx plus e to the sine inverse hx. Okay? So we have that. So you first find the inverse function, and then you what? Differentiate it. Okay? Limit of that. Alright? And then you finally, so it's 3 steps to apply this L'Hopital's second rule. You find inverse, and then you differentiate, and then you plug in the original function. 3-step process. Okay, and you, of course, go upstairs, downstairs, it switches. Okay, you find an inverse, which is x, and you differentiate, which is 1, and you plug in the original x. Well, it's a constant function, so it's 1, right? And you move it upstairs or downstairs. So yeah, 4-step process. 4-step process, okay? All right? So what is this when x go to infinity? We already know by looking at this guy here. Yeah. As x go to infinity, it goes to infinity. That's all we need to know. All right? So e to the something that goes to infinity and plus e to the something that goes to infinity. Well, here we actually have minus. All right? Let's see. Did I make any more mistake? Okay, we find the 4-step process. We find the inverse function, which is inverse of inverse is original, right? So yeah, the original thing, right? So that's the inverse. And then we differentiate it here. And then we plug in the original function. Yeah, there. And we know this whole thing go to infinity. Okay, so e to the infinity, yes, that's infinity. And this whole thing, yeah, e to the minus infinity becomes 0. So yeah, 2 over infinity, yeah, some kind of infinitesimality, okay? So that's that. And it makes sense. Why? Why? Because, yeah, this is a logarithm function, okay? So, yeah, it will be slow infinity. And x, that's faster infinity than logarithm infinity. Okay, so small thing divided by big thing, yeah, it becomes some kind of infinitesimality, so it makes sense. Okay? We got it. We just avoided differentiating this whole thing. I mean, it's not too bad, but it's easier to use the our L'Hopital's second theorem. Okay? This. We just avoided differentiating this whole thing. Trust me, you don't want to differentiate this. Okay? It's, oh boy, no. I mean, we have to use chain rule. It's like 1 over this guy's multiplied by, well, 1 plus differentiation of this, which is we have to use another chain rule. No, you don't want to do that. Life is short. So yes, L'Hopital's theorem finally proved its value. Sometimes it's easier to use L'Hopital's second theorem because we are bypassing differentiating this inverse function. Because sometimes a function like this, arc hyperbolic sine, differentiating that is nightmare. Okay, it's very difficult. But differentiating its inverse, the original hyperbolic sine function, is a lot easier because it involves e to the x. Differentiating that is same, e to the x. Okay. So that's kind of how they defined e to the x. A function whose derivative is itself. So e to the x, y is equal to e to the x, is like identity in terms of differentiation operator. Like d dx, d over dx. So d over dx differentiation is an operator, and e to the x is like identity of that operator, conceptually. Why? Because you differentiate e to the x is itself, e to the x. Okay? Probably that's how they came up with this Euler's number, e. Yeah, 2.73 something. Okay? Yeah, it's an irrational number. Probably that's the motivation or even definition of e. Okay? So, yeah, we would rather differentiate this guy, hyperbolic sine x, instead of differentiating hyperbolic arc sine. You don't want to differentiate this shit, okay? You rather differentiate the original, I mean, the inverse of this, which is sine hx. It's a lot easier to differentiate, okay? And after that, you plug in the original, hyperbolic arc sine or arc hyperbolic sine x, and it's a lot easier that way. Yeah, so second L'Hopital's rule, it is useful. We just vindicated ourselves by this one example. Okay, and so we'll get over it. All right, and our 3 hours is almost up, so we're gonna finish here, and we'll just continue because what time is it? Like what? Is my phone charging? No, it's in my pocket. Probably like 7 o'clock in Sunday night. 8 o'clock. Almost 9 o'clock in Sunday night, but I took a long nap, so it's not necessary that I go to bed early, so we'll just continue, alright? Because it's my bad. We spent too much time correcting my mathematical error, but at least it's kind of instructional, educative, and pedagogical. It's okay to make mistakes. Because that's human condition. We are bound to make mistakes, misjudgment. Sometimes we mislead people. I mean, I misled you because I didn't know inverse function theorem. I didn't know. Okay. So I misled you for a while, for like a couple of weeks. I'm sorry. But hey, President Trump, President Obama, they made mistake too. Justice Kennedy, Justice Ginsburg. Yeah, Justice Sotomayor. Because they thought gay marriage is okay. They thought gay marriage is legit. Yeah, they misled many people. President Obama, President Trump, Justice Kennedy, Justice Ginsburg, Justice Sotomayor, Justice Kagan. So let's forgive them for misleading us, because they are human beings too. Okay, so it's like Jesus saying, God, please forgive our sins, just like we forgive other people's sin against us. Yeah, let's forgive each other. Okay. All right. So I'm gonna take a picture of this, okay? And then we'll take a break and we'll get back to infinity algebra, if you don't mind. All right. Okay. We have like 3 minutes left. We'll just let this camera run because we only have 3 minutes left, and it will stop in our 3 hour. It will just stop automatically, okay? Because that's the limit. All right. So and then we'll take a break and we'll get back to infinity algebra. Okay? We'll just let it run and finish by itself. Okay? All right. Take a break. If you want to write it down, yeah, go ahead. Stare at it, think about it, okay? But if you want to take a break, okay?